Now, real orbitals, if you remember, we said when we were talking about the spherical harmonics, that with m, when m, absolute value of m is not 0, okay, well, when m is not equal to 0, then you get an imaginary function. Your wave function is imaginary because of this term right here, e, that's e to the I m phi. So when m is plus 1, this is the term that you get. And so you can't really plot that. Okay, what you can plot is the absolute value of psi, or you can plot the real component of psi and the imaginary component of psi. Or to make things easier, what we do is we take linear combinations of functions that have the same m. So 2p plus 1 and 2p negative 1. If we take linear combinations of those, so there's one case where you can add the 2 and the other case where you subtract, then you get an equivalent pair of orbitals that will have no imaginary parts. In fact, in this particular case, okay, when you do this particular combination, instead of e to the I phi and e to the negative I phi, you end up with a cosine phi in your expression. Okay, so and you can see what types of linear combinations you need to generate those real orbitals. Going back to that Davidson site, you'll notice here 3dz squared for that m equals 0, but for let's go back to 2pz. 2pz, m equals 0, l equals 0. But if you want to do 2px, it says right here what you actually have here is a linear combination of two wave functions, okay, two orbitals, one with a plus 1, the other one is a negative, so this plus or minus 1. So your m quantum number for a px orbital is not well defined. Okay, it's a linear combination of wave functions with m equals plus 1 and m equals negative 1. The same thing for the 2py orbital. Okay, now what if we only wanted to look at the orbital that has an m of plus 1? Let's see what this site will give us. And that's what you see. Okay. This doesn't look great. Okay, so this one only pretty much just shows you the real orbitals. Okay, but if you want to look at, let's say, 3dxz, you can see that this particular orbital, look at it from different perspectives, this particular orbital is a linear combination of orbitals with m equals plus 1 and m equals negative 1. Okay, so 3dxz, you'll notice, has two angular nodes, okay, two planes that separates into four lobes. Okay, what are those two nodes? You have your xy plane and your zy plane. Okay, so this is your y-axis right here. So you have an xy plane and you have the zy plane over here. Okay, so xy plane and zy plane are your angular nodes here. And if you look at 3dyz, in this case, you see nodes. Your xy plane is a node, and your xz plane is a node. Yeah. Xy plane and xz plane is a node. Okay, so your x-axis is a node. The intersection of those two planes would be the x-axis. And you see, one good way to remember this is that x doesn't show up in the name for dyz. So, intersection of the two planes is the x-axis. And if you have 3dxy, that's what you see. So you can see that that's a linear combination of wave functions with m equals plus 2 and m equals negative 2. So that's a three-dimensional representation.